you guys doing okay? Excellent. So, hopefully this session will be recorded. We've booked it with the course capture people, but thank you all for coming in person because I think there's a very high probability that it doesn't work out at all, and you all will be going to experience this live on stage as it was always meant to be.
So, a brief word about what this is. This is my attempt to condense everything that you might learn in an introductory to astronomy course into 4 hours. This is just the first half of those 4 hours. We've booked this room from 3 p.m. to 5 p.m. And my hope is that I'll be able to highlight a lot of the main topics that you would be interested in if you're taking an introductory to astronomy course. You know, I would love to motivate you all with thoughts like, this will be on the final exam, but I actually don't think that that's the right way to do things. So as we wait for 3:10 to strike, please indulge me for a brief motivation of what we're actually studying and why we should care about it to begin with. Astronomy is the oldest of the sciences. The mysteries of the sky have captured human imagination for longer than we have historical records. Just watch this video. Stonehenge, for example, is an astronomical clock, actually. It still dutifully counts the days until the equinox, even 5,000 years after its original construction. Now, we don't know who built this monument. We don't know what their motivations were, but we did know that they were fascinated with the sky. And they wanted to build instruments and to be able to understand it and predict it. But this is just one of many examples. These points of light have always captured our attention. Many of our most monumental projects over the history of humanity have been expressions of our appreciation of these mysteries. It's really easy for us to forget because we live in cities nowadays and we don't get to see this as much anymore. But when humanity was tribes of hunter-gatherers out on the savannah, the night sky was incredible. The sheer scale dwarfed even the largest mountains and dominated our perception. It was impossible as a human being not to be obsessed with this. The sky was one of the foundations of nearly every major religion on Earth. All across the globe, people based their spiritual beliefs on what happened up there and built their monuments around them. It has been a central part of every myth, every story that humanity has told about our history and our place in the cosmos. Some thought the sun and the moon were great gods, that the constellations were our mythical heroes or the ashes of our beloved ancestors. But these stories that we've told about the sky have crumbled. They've given ways to newer ones over the centuries, but the stars themselves have remained more or less unchanged. Over this time, we've revised the stories that we tell based on measurement and reason. That is the focus of our class. That's the focus of science. The practice of science, especially about the sky, has been one that has revolutionized the way that we tell these stories all around the world. Here you see astronomers in China. The sky is something that people everywhere on Earth have been drawn to and have attempted to understand. Many different interpretations have emerged, each of them having their own merits and their own flaws. But ancient cultures the world over have built observatories like this to understand the workings of the heavens. And they've used the findings that they've made, the data that they've gathered, to update the stories that they tell about what goes on in the sky. Nowadays, thanks to centuries of this kind of research and the development of more precision equipment, we can describe what's happening in the sky with incredible accuracy. The new stories that we tell are based upon the foundations of physics and mathematics, but I think that they do not lack the emotional power of our more ancient mythologies. Our new description of the heavens is still a story about who we are and how we got here. This is my attempt to outline some of the central themes of that description, some of the central ideas, the players in that story that we tell. Like I said, this is just part 1 of 2. And I've broken it into 3 main ideas. The first thing that you need to understand if you want to understand our story of the universe is gravity. So we'll begin with gravity. If astronomy is the study of these weird dots in the night sky, then gravity is our best description of how and why these dots move. This is a bit reductionistic, but this is the gist. Gravity is a central part of the story that we tell about a world. It is our origin story. It's a branch of our more modern mythology. And it's a description that has evolved a lot over the centuries. The history of astronomy is really closely related to the history of gravity. As we gather better data, we can make more accurate descriptions of the motions of the sky. But let's begin at the beginning. If you were to sit back and watch the night sky for just one night, this is what you would see. Let me just let this play for a moment. You see here the North Pole, and all of the other stars seem to be orbiting around it. To a first approximation, it looks like everything is just spinning around the Earth, like everything is fixed on this great geocentric dome or sphere that is orbiting around the line between the North and South Pole. Many of Earth's, most ancient cultures imagine that all of the light from the night sky was from the surface of such a great sphere. And this description modeled most of the behavior that they observed. To that extent, it was a really great description. But it didn't capture everything. If we look more closely, over the course of a year, the sun seems to move against this background of distant stars. Not everything spins at the same rate. The moon as well moves against this background of distant stars. And as people watched more closely, they noticed that the sun and the moon were not the only things that moved against this background. The Greeks called them wanderers, or planetes. It's where we get the word planet. These wandering stars, over many years, seemed to change where they were against the background of the more distant stars. These were immediately singled out as being important, as being unique and special, and they were named in honor of the gods because of how incredible they seemed to be. They were, like everything else, a foundational part of the story that humanity told about itself. The best approximation to make sense of this was to imagine that each of these wandering stars had a sphere of its own, and that it orbited the Earth at its own pace. Now, this alone was a revolutionary concept, right? This was a radical acceptance of the idea of change outside the motion of the Earth. That there could be motion in the heavens was on its own a radical new idea. And this explained most of what we saw. These wandering stars rose and set at their own pace, but everything seemed to orbit around the Earth on these concentric spheres. This story, this change in how we told a story about ourselves, represented the beginning of a golden age in science in nearly every corner of the world. Many of the biggest names in the history of thought were big proponents of this geocentric model. People who were famous for questioning the basic assumptions of reality never even considered questioning this because it seemed so obviously true. And it was a really incredibly successful model. It represented an enormous leap forward for humanity and for the scientific method, updating our beliefs based on data. Complex new instruments were made based on this theory to predict the motion of these wandering points of light and even use their motion to measure the passage of time. It was incredibly powerful, but it did not capture everything. The concentric spheres were not the end of the story of gravity. It didn't get everything. Stars would usually travel eastward through the sky amongst the background, but sometimes they would double back for just a moment before continuing on their path. After many more careful measurements of these motions, measurements that lasted generations for many of these outer planets that take 80 years to complete a single orbit around the sun, after many more measurements, it was found that these planets were kind of up to no good. Their orbits were not perfectly circular, but they still did seem to transit around the Earth in a generally cyclic, nearly circular way. So there was an amendment which was made. Astronomers cooked up new modifications to this theory of motion to account for the peculiar behavior of these wandering stars. These were epicycles. And this was a really weird and description, but it was seemingly more accurate. It captured and predicted the motions of these planets much more accurately than the simple concentric spheres model did. And this was coming at a time when these predictions were incredibly valuable. Humanity was all of a sudden hungry for predictions about things like when exactly Venus would be in retrograde. It was widely believed across many parts of the Earth that the motions of these planets were somehow auspicious, and that there were certain times that were better, for instance, to conceive babies, so the planets would be doing certain things when they were born. People put a lot of effort into making these predictions as accurate as possible. And as they did, this became the default assumption, and it survived a millennium. It was incorporated into the foundational story that we told about humanity's origins. Here, for instance, is God depicted creating the sun and the moon in orbit above the Earth. And this was something that survived in our modern canon for a very long time, but not forever. Eventually, there was this great conflict within the Church of Europe, and all of a sudden, the foundations were being questioned. It was a really great time to have a new idea, and it was an especially good time to question the centrality of humanity's place in God's great cosmos. Astronomers like Galileo challenged the Earth's position at the center of the universe. And while he was sentenced ultimately to house arrest, his ideas caught on. To make a long story short, the sun became the new center of the cosmos. Now, this model was a lot simpler. It was a lot more elegant. And it still had all of the incredible predictive power that the epicycles did. You could still predict exactly when Venus would be in retrograde with a model like this. But the mathematics that underlied it was more elegant. Everything moved about the sun. And the sun was still close enough to Earth that it was not a great demotion on our behalf to imagine that we were just a little far offset from the center. This was a great model of the heavens, but it was not the end of the story for gravity. People created, like before, incredible instruments that they could use to predict the motions of the planets in this way. But it was not the end of our description of gravity. In fact, you could argue that, this point in history was really just the beginning of gravity. Gravity as we see it today, as this force that pushes and pulls on things. That story was just about to begin. These little inaccuracies were piling up, and there was something really weird going on with these comets that would go on incredibly eccentric orbits around the Earth. This guy, Tycho Brahe, dutifully captured the orbits of these comets, and he found that they were nothing like circles at all. And he couldn't make any sense of this, but he gave this problem to a brilliant student and assistant of his, Kepler. And Kepler looked at this data. He pored over it for years and years. And what he discovered was quite astounding. The orbits of the planets did not have to be circular. They could be any of these elliptical shapes, just like the comets. And he found that there was actually a relationship between the orbital period, how long it took for something to complete a cycle around the sun, and how far it was from the sun. This was one of Kepler's laws, that the period squared is related to the distance from the center cubed. But he also noticed something really critical. The closer to the sun the thing is, the faster it orbits. Take a look at this pink orbit here. As the object is nearing the very far edge of its orbit, it begins moving very, very slowly. But as it gets drawn in, it speeds up, it accelerates. As it moves closer and closer to the center, the sun, it moves much, much faster. Now, Kepler thought this was kind of like a push or a pull. It seemed like the sun itself was yanking on these distant planets as they were completing their orbits. But he couldn't quite put this into mathematics. He was able to describe with exquisite detail how these planets moved along these elliptical orbits, but he could not quite describe why. But he and his friends gave this problem to another brilliant young man, Isaac Newton. And Isaac Newton was able to look at this and come up with a revolutionary understanding of the way that force works. Isaac Newton, given this problem, crafted our newest description of gravity, the description of gravity that we still think of today. But to do that, he had to first really quantify how to describe force and motion in general, not just in the heavens, but here on Earth as well. This was something he was inspired to do based on the motions of these planets, but something which has enormous descriptive power here in our everyday life on Earth. The ideas that he came up with are often written down in the form of these 3 laws. If no force acts on a body, its speed and its direction of motion remain constant. This is like if you push something in a vacuum, it'll just keep on going forever. That's the first. The second is that he rigorously defined what the notion of force is anyway. And he related this notion of force to the idea of mass and to the idea of velocity and acceleration. He said that a force is how hard you have to push something. And the way that you can define a force is by the mass of the thing that you're pushing and how quickly you're changing its velocity. And the final thing that he noticed, which was really incredible at the time, was that whenever 2 bodies interact, they exert equal and opposite forces on one another. So I want to do a little bit of a detour for a second before I move on with the history to actually demonstrate this for all of you. I find that it's much better to actually do this in a tactile way than to just write it down. So I need 2 volunteers from the audience, preferably 2 of you who are friends so that you don't hurt one another. Please raise your hand if you'd be interested in doing something live. You 2, excellent. So I have these 2 chairs for you. If you came to lecture 12 in the beginning of the year, you remember how this works. But if you don't, you're in for a treat. So let's demonstrate the first. You 2 just stay over there for a moment, and I'm going to pass this chair to you. An object in motion remains in motion until you come along to stop it. Now, there's friction with the floor in our case, and this is why nobody came up with these ideas nowadays. But if you take this chair and accelerate it towards me, take it and push it, you'll notice that it continues to move until I come along to stop it. Continues to move until you come along to stop it. But the other most critical idea is that pushing it requires a different amount of effort based on how heavy the chair is. So take a moment now and just push the chair just a little bit while it's empty. Do you want to give it a turn?
Pushing the chair?
Absolutely. Push the chair. Yeah. Was that very difficult? Would you do me a favor and sit in the chair? So now what we've done is we've changed the mass of this object which is being accelerated. And so what I want you to tell me now is, do you have to put more or less effort into pushing the chair now that its mass has changed?
More effort.
More effort, right? This is law number 2. Force is equal to mass times acceleration. You accelerated the chair by the same amount. You changed its velocity by the same amount. But since the mass of the chair was different, you had to push a lot harder. Do you want to give that a try yourself? Just confirm. So you remember what it was like to push the chair when it was empty. Let's see if this feels different. Require more effort? Yeah. So that's law number 2. If you change the mass of the things involved, you have to push them a lot harder. This was a really radical idea. This is how force itself was defined. Force is a change in momentum. And now the last thing which is really critical is that every action has an equal and opposite. It's hard to notice when you're standing here on the floor with your feet gripping the ground, but it'll be easier to notice if you're both able to move. Now, is it possible for one of you to push the other without being pushed back yourself? You can use your feet to push off. Absolutely not. You both have to move. You both experience a force. There's no scenario in which you push on something and it doesn't push back on you. To demonstrate this further, like I can try to push this desk, but it will always push back on me. These are Newton's 3 laws of motion. That'll be all for So please give a round of applause to these 2. It's always really wonderful to have volunteers on stage. But so these are Newton's laws of motion. They were really radical at the time. People thought for centuries that things had a natural state of being at rest. You notice when I pushed the chair before, it came to rest by itself, seemingly without any kind of external force. This was because on Earth we have friction. Friction interferes with everything. Friction is the subtle little force of the wheels on the floor that slow the chair down almost imperceptibly as it travels. But Newton realized that out in the vacuum of space, there would be no such friction. And if there was no force to act on these bodies, they would move continuously, forever, without being stopped. But this still is not a description of gravity. This is just a description of how things move here on the Earth. But so Newton did a lot of thinking about this, and he thought, could it be the same force that pulls things here down on the Earth, that pulls the moon around in the orbit around the Earth? Everything on Earth seems to fall at the same rate. Does the moon also fall at this rate? Well, he had to think about this quite critically. He remembered that based on his other measurements of forces, he said force equals to mass times acceleration. How could there be such a force that pulls everything at the same rate here on Earth? Just to get a sense of what I'm talking about, here I have two different objects of two very different masses. This one is much heavier than the other one. But if I take them and I drop them at the same time, they fall at the same rate, air resistance notwithstanding. This means that the force that pulls on the heavier thing must be much greater than the force that pulls on the lighter thing. Otherwise, their accelerations could not be the same. And because forces are equal and opposite, not only is the Earth pulling on this heavy thing, this thing is pulling on the Earth as well. So if the strength of gravity is proportional to the mass of this object, it should also be proportional to the mass of the Earth itself, the object doing the pulling. And so this was a really revolutionary idea, but it was also not the end of the picture. The other idea was an insight that Kepler had, that Kepler noticed that when you were closer to the sun, you seemed to be moving faster. And while an object was further away from the sun, it seemed to be being pulled not as much. Kepler wondered if this could be described by what was called an inverse square law, where the strength of gravity might fall off with the distance squared. Say, if you got twice as far away, the strength of gravity would be 4 times weaker. This inverse square law idea was already cropping up in the world of physics in optics. Light, as we'll talk about later, behaves according to one of these inverse square laws. And so Newton combined that idea of gravity falling off with distance squared with his incredible insight about force versus mass and acceleration. This notion that if gravity is a force, it must be proportional to both the masses of the objects involved. This is still one of our most incredible, one of our most descriptive pictures of gravity. The force of gravity is proportional to the mass of the object being pulled, the mass of the object you're looking at, that is, the mass of the object pulling it, divided by the distance between them squared. And gravity can only pull on things inwardly. You see here, gravity is the orange arrows. They only pull something towards this object in the middle. Gravity will never be a push, it'll never push something away from you, and it will never tug you in any direction other than directly towards the center of the thing doing the pulling. But in this case, you can still have an orbit, as you see here. The green arrows represent the velocity at the time the snapshot is taken, whereas the red arrows represent how it's actually being moved, how that velocity has been updated according to the acceleration inwardly. When you do this in a continuous way, when you apply calculus, this theory of taking all of this motion and dividing it up into infinitely small pieces, you see that what you get is a circle. Orbits, so says Newton, are like a fall and a miss. He has this incredible thought experiment where he says, imagine you took a cannon to the top of a really high mountain, and you fired a cannonball pretty fast. Well, that cannonball would, travel pretty far, but eventually, like everyone knows, it would fall back into the surface of the Earth. Perhaps you could even fire a cannonball so far that it went beyond the horizon, all the way around and landed on the other side of the Earth. But he says, if this description is right, if gravity only ever pulls inwardly, then I ought to be able to fire the cannon fast enough that the cannonball would fall all the way around the world and end up right back where it was. If there was no friction in outer space, there would be nothing to slow this cannonball down. It would lose no energy and would return to exactly where it started with the same velocity and complete the cycle over and over and over again. This description was incredibly powerful, and it could account for the Kepler's laws that were already discovered, dozens of years beforehand. Gravity, as described by Newton, was this delicate balance between the inward pull and the rotation. And using this concept, he could re-derive the same laws that Kepler had earlier. So allow me to demonstrate this for you. So what you're seeing here is how orbits, the closer you get, the faster they seem to be moving. Remember, this is what Kepler said. The period of an orbit depends a lot on the distance it is away from the center. Not only does the orbit itself get larger, so it takes longer to go around, it also is the case that you're moving slower along that orbit, so it takes a substantial amount of time to complete one transit, the further away you get. And the way that Newton was able to re-derive this was by thinking about it in terms of centrifugal force. Centrifugal force is this force of rotation. It's like when you're spinning really fast and your arms want to fly out. Everything wants to move away from your perspective, from the center of the rotation. So allow me to demonstrate that for you briefly here. What I have in my hand is a planet. And this planet, if I spin it over my head, follows the path of an orbit. But if I let the planet come to rest, and I drop this weight, which I hold in my other hand, this weight pulls the planet inwardly. This is a rope. It can only ever pull something inwardly. I cannot, with a rope, pull something side to side. I can start it up by doing something like this. But what I can demonstrate to you is that there is a precise balance that can emerge between the outward force, the centrifugal force that's trying to pull this planet away from the center of its orbit, and the inward force of gravity, represented here by the weight. Now, if I drop the weight, I can find a critical speed where there's a balance. The centrifugal force outwardly balances the force of gravity inwardly. And as I change the diameter of this orbit, the radius, I have to move a lot faster in order to keep that balance. Oh, please don't hit me. Let me do it on this side of the room so that everybody can see. And I'll narrate it again as I do. If I start this in an orbit, there's a balance that can form between the outward centrifugal force and the inward force of gravity. This balance is a function of the radius of the orbit. When the radius is large, it doesn't have to spin very fast. But as the radius gets smaller, I have to spin it a lot faster to keep it from falling inwardly. It is this way that Newton was able to re-derive Kepler's laws. He got, surprisingly, the exact same result, except with one incredible modification. When Kepler looked at these laws through his lens of data, he looked at all of the orbits that Tycho had captured over many dozens of years. He noticed that there was a relationship between the period and the radius, the average distance of these orbits, but he couldn't understand what the constant was that related one of them to the other. But using Newton's new theory of mathematics, Newton could actually derive this constant k from scratch, based on the other relevant constants involved. You don't have to remember exactly what this constant k is. You don't have to write it down. It will always be given to you. But what I want you to remember is how incredibly powerful that is, to come up with a theory of motion that's able to describe something that before was just a fudge factor. He was able to derive from first principles exactly how these things should move, and was able to come up with something that was very similar, but actually even more general than what Kepler had described before. Now, that's not to say that Kepler was wrong. He got it pretty close. If the mass of one of the bodies involved is much, much heavier than the other body involved, for instance, the sun is much, much more massive than the Earth, and even much, much more massive than Jupiter, then to a good approximation, the sum of the two masses is pretty close to just the mass of the first thing. So if you plug that into the denominator of Newton's description of this constant k, you get what Kepler found, which is that k really is a constant, at least to an excellent approximation when you're talking about orbits in the solar system. But what Newton was able to find was something much, much more general, something which could describe orbits not just of bodies around the sun, but say of the moon around the Earth, or of moons around Jupiter. or even the motions of exoplanets, although he did not yet know of those. And his description of gravity allowed for these weird lopsided orbits. His orbits did not have to be perfectly circular, even though the ones that I just showed you here with the demo were. His theory allowed for orbits to be ellipses, just like Kepler had described. So I want to see who's been paying attention. Again, this is meant to prepare you for the kinds of questions that you might, for instance, see on an exam. So it would be no use if I just stood up here and talked to you the whole time. So I hope that you all brought your ABCD cards. This will be the first of many. How does the strength of the force of gravity change when you double the distance between two objects, according to Newton's theory? Take a few moments and then hold up the card that you think corresponds to the correct answer. Ready? Excellent. Excellent. So I see almost entirely blue Ds. That's exactly correct. Like I said, gravity is one of these inverse square laws. If you go twice as far away, the strength of gravity falls off by a factor of 4. If you go 10 times further away, the strength of gravity falls off by a factor of 100, etc. Okay, so let me pause now to take any brief questions about gravity before I move on to the next main idea in our description. Is there anything that any of you want to know about what we've just been talking about gravity? Yeah?
Wait, sorry, could you reiterate for the acceleration of gravity to be the same, how the force has to change?
Absolutely I can. So this is a really critical insight that Newton had. And what Newton noticed was that everything on Earth seems to fall at the same rate. This is actually something that Galileo noticed many years before him. But what that means is if you take two objects which have very different masses, for instance, I just have this battery and this glove, which I'm both going to use later, and I hold these at the same height, and I drop them simultaneously, they fall at the same rate. They accelerate downwards at the same rate. So why is that interesting? Well, the description of gravity that Newton had was one where force was something where it was really dependent on mass and acceleration. If you had a force which was constant, let's imagine that the force of gravity was constant for every object on Earth. If I had something which was really light and something which was really heavy, and I dropped them both at the same time, the light thing would fall a lot faster because the force would be the same, but the accelerations would be different. So Newton's critical insight there was to realize that the accelerations were always the same. And what that meant was that the force of gravity had to be a function of the mass. It had to be that the Earth itself was pulling on the heavier thing more. Say if I have one thing that's 10 times heavier than the other, gravity must be pulling on that thing 10 times harder. That was the critical insight. Excellent. So what I want to finalize to say is that gravity is a remarkably powerful story. Like I said, gravity is an enormous central part of our story of our origins. It's the centerpiece of our explanation of how Earth and the planets were formed. This is how we think the stars were formed as well, and why we think the planets began in an orientation where they were all orbiting around the sun. Now, this theory of the formation of protoplanetary disks and planets is a whole other can of worms that we could open, say, during office hours. But what I want to really emphasize is that gravity has an incredibly central and important place in our story of the history of the universe. But now I want to move on from gravity because we have a lot to get through today. We're trying to pack basically the whole first half of the course into one day. I want to talk about light. Now, light is something that you must have an understanding of to understand astronomy. Astronomy is the science of light. For almost the entire history of astronomy, the only information that we've been able to have about things in outer space is via light. If you're a geologist, you can go to a sample and you can break it apart, you can feel it, you can test it for chemicals, you can smell it, you could taste it if you were really being silly. But in astronomy, we only have vision. And to gain any kind of information about what's actually out there in the universe, we need to understand how vision works. We need to understand what light is. So, what is light? Well, let's start with the absolute basics. What do we know? All of you are in the audience here, you're watching me, you're able to form a picture in your head of who I am and what I look like and why I'm waving my hands about all crazy like. Light has to be something that transmits information from me to you. You don't have to come over here and make physical contact with me. Somehow light is getting from point A to point B. But the most important thing aside from that you should know about light is that light actually has a speed. Transmitting this information takes time. Although it feels like it's instantaneous when we're here in this much more human scale context. The speed of light is actually pretty slow. On the scale of the Earth, it's still quite fast. The light can orbit around the entire Earth 7 times in a single second. Light can even bounce between the Earth and the Moon in just less than 1.5 seconds. But once we start talking about things, even the scale of the solar system, the speed of light becomes incredibly important. Light takes 8 entire minutes, actually a little bit more than 8 minutes, to travel from the sun to the Earth. If the sun were to turn off all of a sudden, we on Earth wouldn't even be able to notice for 8 entire minutes. But the next question that we have to ask is, okay, well, it takes some time for light to transmit information, but what kind of information does light actually carry? How is it that we can look at whatever's happening in the space between you and I and understand what's going on someplace entirely different? How can we actually learn anything from light? Well, the information that light carries is all about color. Color tells you what things are. Color is how we gain intuition into how things behave and what they're made of and how they're moving. But that still doesn't really answer our question because we haven't answered what is color. We still have to answer the question, what actually is light? And to do this, we have to take kind of a detour from the world of what you might consider astronomy to the world of what you might consider physics. We have to talk about electricity and magnetism. So raise your hand if you've ever rubbed a balloon on your head or gone and bothered your sibling with it. What happens? Do you remember? Your hair sticks up. This is actually really weird. This is something which is everyday. It's something that we accept as just part of the status quo. But in terms of the behavior of everyday objects, this is actually quite strange. I'm normally used to having to pick things up and physically touch them in order to move them. But when we're talking about electricity, I am able to do a little bit of action from a distance. I'm able to transmit some kind of force without making physical contact. When you hold this balloon next to your sibling's head and their hair sticks up, you are pulling on their hair without actually touching it. That's so incredibly bizarre. It's crazy that we take that for granted. And the same is true for magnetism. Here I have in my hand 2 magnets. I don't have to bring them all of the way together before one of them connects to the other. This magnetic force seems to be able to be transmitted throughout empty space. If I went into the vacuum of space and I did the same experiment, I would get the same result. This also is incredibly bizarre. This is force at a distance. And this leads us to a theory of electricity and magnetism that involves these ideas of force fields, these fields that permeate all of space and time through which these forces can be transmitted. We imagine that the force field around a bar magnet looks like so, where the space itself seems to want to move things towards the South Pole and away from the North Pole according to their magnetic polarization or their magnetization. And something very similar is true about electricity. We imagine that there is an electric field around charged particles that wants to move other charged particles towards them or away from them. This is the foundation of our theories of how your cell phones work, of most of modern technology, but it's also an enormous foundation of astronomy. These 2 fields are part of our description of light. It turns out that the electric and the magnetic fields are actually related. They're like 2 sides of the same coin. And allow me to demonstrate that for you just now. I'm going to put on a glove for this so I don't hurt myself. Here I have a couple of things. I hope that everyone can see what I'm doing here on this table. Sorry if you're way over there. In one hand, I have a battery. This is just a standard D battery that I got at Ace Hardware. And what I have in this other hand is just a screw with some wire wrapped around it. Now, if I take this and I go to these other screws, I can dig around in them all I want. There's no magnetic interaction between these things and this thing. But if I introduce some electricity into the equation, I connect the top and bottom of this with my battery, I'm actually able to pick these up. If I let go of the electric charge, I stop the current from flowing, they fall back down to the floor. What's happening here is that a change in the electric field induces a change in the magnetic field, and vice versa. If I were to do the opposite, I could have something like an this is what's called an electromagnet. I could also have an electric motor, where I induce an electric current. I create a change in the electric field. And by doing that, I can create a change in the magnetic field. Or I could take that same system and run it in reverse, creating a change in the magnetic field by spinning my rotor, and therefore creating a change in the electric field to charge a battery. This is how most electric charging systems work. These two fields are twins of one another. Changing one can change the other, and vice versa. If I were to take a charged particle and move it around through the electric field, I would induce changes in the electric field. And what we just saw is that changes in the electric field induce changes in the magnetic field, and back and forth and back and forth. So one would change the other, and back again and back again. And so what it looks like if I take such a charged particle and make it wiggle around is I see something like this. Oscillations. Changing one changes the other, and back and forth and back and forth. If I allow this to keep playing out, you can see that these are like ripples. Shown here is the strength of the electric field, I think, as it moves one way or another. If I take just a one-dimensional slice of this, I can see that these ripples propagate like waves. Once you get far enough away from the source, they travel through space just like sine waves. These waves are a lot like the waves that you might see on the surface of the ocean. They can be described by the same parameters. They have a speed at which they propagate, and they have a wavelength, a distance between one peak and the next. And like I said, these are just oscillations in the electromagnetic field. Inducing a change in one induces a change in the other. This is light. This was an enormous discovery back in the day. People working on electricity and magnetism were already overjoyed when they realized that those two ideas could be unified together. Somebody noticed just by happenstance that you could have this very interesting solution to the electromagnetic field equations, that you could have ripples that would propagate through empty space that could transmit information. And by then they already knew about light, and they had actually measured the speed of light to a pretty high degree of accuracy, but they still had no idea what it was. And when the people working on electricity and magnetism got to the stage, and they had measured the strengths of those two forces and the relationship between them, they were actually able to calculate the speed of light from first principles, and they got it, to their astoundment, exactly correct. This is what light is. This is what is carrying the information between me and you. This is the physics that allows you to see what I'm doing here up on stage without having to actually come up here yourself. It is incredible. Just these ripples through the electric and magnetic fields, the fields that permeate all of space and time, that allow me to do things like this with my electromagnet, are able to transmit light across incredibly vast distances. So now we have a good description of what we're actually talking about when we say things like color. Color is wavelength. Color is the distance between these waves. You can have waves of any length through this electromagnetic medium. You can have them be incredibly long, kilometers long if you wanted to, or incredibly short, just micrometers. There's no real limit. But each of these waves behaves very differently, and each color can tell us something unique about its source. It's worth noting also that the range of wavelength that we can see is actually an incredibly narrow subset of what is actually possible. You can have waves that are in the visible range, which are about a micron in diameter, a few hundred nanometers, much, much shorter than a meter, barely the width of a hair. But you can have waves that are meters long, like radio waves. This is what you're listening to when you turn on the radio in your car. Information being transmitted through space in the form of incredibly long waves of light. But you can also have incredibly short ones, like X-rays. So one thing that I want to demonstrate is that this idea of color is really closely linked to the idea of energy. And to be able to do this demonstration, I need another 2 volunteers from the audience. I have 1, 2. Can you both come up here? Thank you again for volunteering. You volunteered to do this, having absolutely no idea what I'm about to ask you to do. But here's what I'm about to ask you to do. Hold on to one end of this and come way back here. Can you come further this way so that the people behind the podium can see? And then you can hold on to the other end of this. So stretch this across the entire auditorium stage. And then, just to make this as one-dimensional as possible, please take a moment to just kneel on the floor so the slinky is totally flush. This is our simulation of the electromagnetic field. This is the slinky field, or just a one-dimensional slice through it. And what you'll see is the fundamental physics is actually quite similar. If you are to make a perturbation to the slinky field at one point in space, it can travel all the way across to the other point in space and be received over here. So one thing that I want to establish, okay. The slinky field is a little bit feisty. I'm going to bring it back over to you. Don't worry about it. So one thing that I want to establish before we talk about energy is I want to revisit this notion of speed, the speed at which waves travel down the slinky. We want to, confirm for ourselves, just for the sake of our sanity, that this is, in fact, something which is constant. We've heard our whole lives that the speed of light is a constant. So do me a favor and create a really long wave by going like this. It takes about a second for this wave to travel from one end of the auditorium to the other. Now stop, and then do the same thing, but really fast. Notice that it took the same amount of time for information from one end of the room to be transmitted to the other, regardless of the wavelength involved. But now I want to return to the central idea, the idea of color versus energy. So color, like I said, is really just a feature of the wavelength of these waves. Longer wavelengths are going to appear to our eyes as redder, and shorter wavelengths are going to appear to our eyes as bluer. But that doesn't mean that each one of these waves carries with it the same amount of energy. Some of them could carry more energy than others. And to figure out which ones are which, we can actually do this experiment for ourselves. Now that we've established that the slinky behaves like the electromagnetic field, we can do an experiment. So try sending a really long wave down, just back and forth twice. So just do more continuously. Wonderful. And now pause. So think about how much energy it took for you to do that. Right? Was that something that was relatively easy or relatively hard? Pretty easy? What happens if you want to create a much, much shorter wave? You'll have to go like this. Huh? Yeah, shorter wave. So keep the amplitude the same. Move your arm back and forth the same amount, but just faster. Faster. It's more effortful, right? That's starting to be a workout, and we've only really doubled or halved the wavelength. Do you want to try this for yourself to confirm? We don't just want one data point. Send a really long wave. Excellent. And now stop. Now try sending a much shorter wave. Perfect. So which of these, in your estimation, required more energy on your part? Definitely the shorter one. Yeah, so this is something that we can actually write down and say as true. So stay there for just a second. We're going to move on to the next idea. The wavelength and the energy are inversely related. If I were to double the wavelength, make the wave twice as long, the amount of energy that it would carry would change by a factor of 1/2. It would carry only half as much energy. If I were to do the inverse, if I were to say, make the wavelength 4 times shorter, that would mean that I'd be carrying 4 times as much energy. So this is a proportionality that's given to you on your homeworks and on the front page of the exam, but I don't want you to have to think about this. I don't want you to have to look this up. When you think about the relationship between color and energy, return to the idea of the slinky. Imagine yourself trying to wave the slinky back and forth really fast in order to create a wave which is of a shorter wavelength. You'd be putting in a lot more energy. We can also rewrite this as a direct proportionality. So rather than saying if I double one, I have the other, we can think of a new description of color to be able to relate these one to one. So instead of thinking about wavelength, let me think about frequency. Frequency is if I'm standing at just one point in space, how frequently does this point in space oscillate? How many cycles does it go through per second? So do me a favor and send a long wave. So if I'm looking at just this point in space, it oscillates maybe once a second. It goes up and down, even a little less than once a second. So when I have a really long wavelength, I have a really short frequency. And if I send a much shorter wave down, the frequency becomes much faster. It goes up, down, up, down, up, down, up, down, up, down, up, down. So by decreasing the wavelength, I have increased the frequency. And it's pretty easy to see that these two things are inversely related to one another too. So this is a huge help for us. I can say that the frequency is then proportional exactly to the energy. If I double the frequency, I double the energy. And an important thing to notice is that it's not just a proportionality. You can write it like an equation. The frequency and wavelength are related to the speed of light. If I were to change the speed of light in the system, I would change the frequency. And to make this more clear, I'm going to ask you to stand up and make the slinky a lot less tense. So stay where you are and come about halfway closer. Perfect. So now we still have the same slinky, but the tension in the slinky has changed. And here's what I want you to notice. Try sending a wave down now. Notice that the speed of the wave propagation is now much slower. The waves travel not nearly as fast as they did before. And if I were to send a wavelength of the same one that you were sending before, I would notice that the frequency would be different too. So try to send another wave that was as long as the one you did before. So this was a frequency that was pretty fast. But now that I've made the speed of light slower, I've made the frequency slower too. Okay, please give a round of applause to our two excellent volunteers. Thank you very much for coming up on stage. You can just put that on the floor. Yeah. No. Okay. Okay. So we've established a bunch of things so far. That's completed basically our picture of what light is. Light is ripples through this electromagnetic fields. But it doesn't tell us very much about how light actually tells us anything about the things that we're looking at. But first, I want to make sure that we're all on the same page. So let me ask by way of review, what happens to the wavelength of a photon if I double its energy? If I double the wavelength of a photon, what happens to its energy? Think about this for just a second. All right, hold up your cards. Excellent. We're all absolutely in agreement. The energy of the photon is half. This is what I just said. And what about the frequency? If I double the frequency of the photon, what happens to the energy? All right, I see a little bit of disagreement, but overall we're still on the same page. If I double the frequency, I also double the energy. But we still haven't answered this question, where does light come from? How is light emitted? I showed you this picture before of taking an oscillating particle. This is like some electrically charged thing moving back and forth in space. And what we're going to try to establish is what are the different physical processes in nature that can cause something like this to happen? Where in nature are there electric charges that wiggle? So the first thing that I want to establish is thermal radiation. And to do that, I have to put my glove back on. So what on earth does heat have to do with light? So here I have this tiny little metal piece in my left hand. And in my right hand, I have an industrial blowtorch. So what do you think will happen if I heat up this piece of metal? Are you all able to see that? It fades pretty quickly, but for a second there, you can see exactly the phenomenon that I'm talking about. Let me do it again. When the metal is warm, it's emitting light. You're all able to see it back there. And what's really critical is the warmer it is, the brighter this light is. This is something that is incredibly important in astronomy. This is how we learn about stars and their temperature. But so if we want to understand why this happens, we need to answer another one of these questions. We need to answer the question, what actually is heat anyway? Why is it that the process of heat, why is it that temperature has any effect on light? So I want to think about this picture. This is what temperature is. Heat is all about microscopic random motion. What you're looking at is water molecules. On the top, they're in ice, and in the bottom, they're in the form of water. But in both cases, you can see that they're not absolutely still. In both cases, they're wiggling around a little bit. Due to just the kinetic energy of each of them individually, the substance carries a bunch of energy. This energy is not in the form of all moving in one direction or all moving in another direction. It's microscopic motion, all of these things bouncing off one another. And what they're doing is just like that charged particle that we talked about, they're wiggling back and forth. Some of these particles are moving faster than other ones based on the temperature, and others are moving slower. But generally speaking, the hotter something is, the faster these particles are moving on average. And hot things are going to glow due to these microscopic motions. Every particle disturbs the electric field as it moves. Every one of these particles has an electric charge associated with it, and as it bounces around, it tugs on the electromagnetic field as it goes. So let me just do a very brief review question. This is based on the earlier idea that we did with the slinky, this notion of color versus energy. But now let me think about it in terms of temperature. If I have something which is hotter emitting higher energy photons, will something which is hotter appear more red or more blue? Very briefly, just hold up your cards for this to make sure everybody's paying attention. Something which is hotter appears more red or more blue. Everybody is in agreement. Something which is hotter appears blue. Now, this is pretty counterintuitive. We're used to, in our everyday lives, thinking of like blue as the symbol for cold and red as the symbol for hot. But like, if you look at a picture like this, it's common sense that the blue part of this flame is the hotter part. But we can take this idea and we can describe it more mathematically, more rigorously. What we're talking about when we say the color of something emitting due to its thermal radiation, we're talking about a distribution of colors. This thing isn't emitting one single color. Like I said, some of the particles are moving faster and some are moving slower. We're talking about the peak wavelength, the characteristic speed of that temperature, and therefore the characteristic energy that a photon leaving this object would have. What we notice is the hotter something is, the shorter that peak wavelength. The shorter the most common wavelength is, the bluer the most common color. We can write this down like a proportionality too, just like all of the other proportionalities we've written so far. The temperature is inversely related to this peak wavelength. Okay, wonderful. So there's another feature of this, though, that I hinted at before that I think is relevant. It's incredibly relevant in astronomy. Not only as I increase the temperature, do I increase the peak wavelength, do I make it bluer, I also make it brighter. You can see that when you look at these curves. Something which is 3,000 degrees Kelvin is not emitting very much light at all, if I plot the amount of light versus the wavelength here. It's emitting a little bit, and you can kind of see where the peak wavelength is. But something which is emitting twice as much is emitting an enormously higher amount of light. That's saying that the luminosity, the amount of total energy being emitted in the form of light, is incredibly dependent on the temperature. If you take like a thermodynamics class, you'll be able to see why this is, but I'm just going to give it to you. The luminosity of something is proportional to the temperature to the 4th power. That means it changes enormously if I change the temperature even a little bit. It's incredibly sensitive to the temperature. Something which is just even a little bit hotter will be enormously brighter. So let's do another question here. This is about that idea from before. If I have object 1, which has a peak wavelength of 200 nanometers, and object 2 with a peak wavelength of 600 nanometers. Which of these is the case? All right, ready? All right, we're a little shyer about this one, that's okay. But overall, we have consensus. The correct answer that I saw almost most frequently is answer C. Object 1 is 3 times hotter than object 2. This is one of those inverse proportionalities where you can notice that the peak wavelength of object 1 is 1/3 of object 2, which means that it's 3 times bluer and therefore 3 times hotter. Now let's do another one of these related to this notion of luminosity and temperature. If I have object 1, which has a temperature of 500 degrees Kelvin, reasonably hot, and object 2, which has a temperature twice that of 1,000 degrees Kelvin, which of these is the case? Hold up your cards. Excellent, okay. So we're willing to work with this notion of proportionality to the 4th power. Object 2 is 16 times as luminous as object 1, just because its temperature is different by a factor of 2. So understanding this idea of thermal radiation is incredibly useful in astronomy. When we look at stars, as we'll get to in a second, thermal radiation accounts for an enormous percentage of the light that we see, an enormous amount of the descriptive power that light gives us over what we see, but it's not all of it. The next idea that I want to talk about is spectral radiation. This is these emission and absorption lines. When we talked about thermal radiation was continuous. It was emitting a rainbow of colors. It was emitting every possible color in the spectrum, except there were some which were more frequent than others. When we talk about spectral radiation, we're talking about a kind of light which only comes in very, very, very specific colors. It can only be exactly this wavelength and nothing else. And to understand why that is, we have to again take a pretty brief detour into the world of quantum mechanics. Now, you can let your eyes gloss over this, but there's something really critical that I want to point out about this picture. What you're looking at here is different energy configurations for electrons around an atom. You can see that there's very many of them, but there's also not infinitely many. There are very specific energy orbitals, different configurations that electrons can have while they're orbiting around an atom. Each one of these different configurations has a different energy associated with it. So you don't need to worry about the weird shape of these bubbles, but you do need to worry about this picture. Inside of an atom, an electron can only exist in very specific energy levels. This is like existing only at very specific steps on a ladder. Like so. I can only ever be standing here or here. I cannot be standing like hovering in midair at any other altitude. The energy that I have is proportional to how high I am, but I can only ever be standing at very specific rungs on this ladder. I can't just be hovering anywhere. This electron is similar. Inside the atom, it can only have very specific energy levels. It's allowed to transition between them, but it can't be stable and long-lived anywhere aside from these very specific values. If it were to jump down from this energy level to the one below, it would emit a light wave. It would go down in energy, just like if I were standing up on this chair, I would have to, lose energy to come up here and to go down. And so when the electron goes down, it has to emit energy because energy must be conserved. And the amount of energy that it emits is going to be exactly related to the difference between the energy levels it jumped between. And so there's multiple possibilities for ways that it could jump between these energy levels. And each one of them has a very different characteristic energy difference. This is the change in energy between one step on the staircase and another. That change in energy, that energy difference, is transmitted out to the universe in the form of light. And since we know exactly how much that energy difference is, we know exactly what wavelength these photons will be. And what's wonderful is that each different element on the periodic table has a different set of energy levels where electrons can exist. That means that it has a different set of possible energy levels that it can interact with, a different set of colors that it can emit or absorb. And that means that we can look at something like a spectrum which only contains very specific colors, or contains all of the colors except those ones, and saying this is something which is interacting with hydrogen, or this is something which is interacting with helium. For instance, if I were to look at a perfect black body source, a perfect thermal emitter, like an idealized star, emitting all of the different colors in the rainbow, and if I were to look at that star through a cloud of gas, I would see all of the colors of the rainbow except those ones that can interact with whatever the cloud is made of. That cloud would absorb only those very specific energies that allow it to jump up, and then it would re-emit them in some random other direction. And if you were standing off to the side of that cloud of gas, and you were looking at the cloud, you would be able to see only those colors. So if you're looking through this cloud of gas, you'd see those colors as missing. But if you're looking at the cloud of gas from some other angle, you would see only those colors as being present. In either case, you can learn a lot about what the cloud is actually made of. Okay, so I know that I just said that all of these colors are very, very specific, but there is actually a way that they can change. For now, I've always been assuming that the sources of light have been stationary, that they're not moving with respect to you. But what happens if they are? Well, in a stationary source, light is emitted in every direction at the same wavelength. Light which is traveling this way goes along its merry way. Light which is traveling the other direction goes along its merry way, and they're indistinguishable. But if I were, say, moving this direction, I were to emit a wavefront and then step towards it, and emit another wavefront, and step towards it, and emit another one, these wavefronts would be compressed. I would have made the wavelength shorter if I'm traveling in the direction that I'm emitting the light. And the opposite is true for the other case. If I'm moving away, I emit a wavefront, and I step away from it, and then I emit another and step away from it. I make these wavefronts further apart. I increase the wavelength. This is something that you can see in this animation. This ball here, as it's traveling, is just emitting waves and concentric shells, but since it's moving as it's doing so, the waves are compressed in the direction that it's moving, and they're stretched in the direction that it's moving away from. This is what we call the Doppler effect, and it's not just something that's relevant for light. It's something that we hear for sound, too. If you hear an ambulance goes by and it goes like, meow, that's the Doppler effect. As it's moving towards you, the frequency is increased. The wavelength is shortened, so you hear a higher pitch. As it's moving away from you, the frequency is decreased. The wavelength is lengthened. You hear a lower pitch. But in light, we're all about color. So if a source is moving towards you, it appears bluer. And if it's moving away from you, it appears redder. This is oftentimes called red shift or blue shift. We can say something even more specific. We want to write this in terms of one of these proportionalities that we've been using. We can say that the change in wavelength is proportional to the speed at which you're traveling. And the way that we write this down is in terms of two different fractions. The change in wavelength as a fraction of the original versus the speed at which it's traveling as a fraction of the speed of light. So what that means is if I'm moving at, say, 10% the speed of light, then I'm going to shorten or stretch the wavelength by a factor of 10%. The way that you can go about calculating this, if you really want to do it by hand, is saying that the difference between the observed wavelength and the rest wavelength as a fraction of the rest wavelength is going to be V over C. So I want to do another test problem to drive this point home. If I measure an absorption line out in space at 550 nanometers, but I know that it should be 500 nanometers if it were at rest, like when I measured it back in the lab, how fast is the source? And is it moving towards you or away from you? Think about this for just a second. Be really critical about whether it's moving towards you or away from you. Okay, what do we think? Good, we have near consensus. It's moving 10% the speed of light away from you. Notice that the wavelength has gotten longer. The wavelength has gotten redder. That means that this is something which is being redshifted. It's something which is moving away from you. Just like in the animation, something which was moving away had larger gaps between the peaks of the wave. Okay. So I want to briefly take questions about light, but then I want to move on to the main event, which is what's actually going on out there in space. Yeah?
Quick clarification about the last one.
Sure.
So if it was, because it was measured at 550 nanometers and it was observed at 500 nanometers, this based off of that, because it was measured at 550 nanometers, we can already tell that it's moving away from you.
Yes, we can tell it's moving away if the light has been lengthened at all. And the next part is to tell how fast is it moving away. And you can come up with that based on how much it's been lengthened. Yeah?
I was wondering about the shape of like wavelengths. Like, why can't they be? I guess like why couldn't they be in a square shape? And then also why it's a photon that's emitted instead of thermal radiation.
Excellent. Okay, good. So this is a really great question. Why is the shape of these waves that travels this weird sinusoid, this smooth shape? Can you have a wave that travels which is shaped like a square? This is a really excellent question. And it has everything to do with the physics of stability. And to think about this, imagine trying to send a square wave through your bathtub. You could maybe come up with a really elaborate contraption to send a wave which was shaped like a square, to make a wave which was shaped like a square. That's something like this. But what I theorize is that that wave wouldn't remain very long. It would eventually become a wave which looks more like what you're familiar with waves in a bathtub, something which is more sinusoidal. And that's because those kinds of waves are more stable. They propagate more efficiently. And so a wave which is closer to that shape will survive for longer. And waves which are different from that shape will evolve towards that shape. That's what's so special about the sinusoid, is it's incredibly stable when it comes to the physics of wave propagation. Excellent question. And the other was, what was it, why do we emit photons when we jump between energy levels? That's a great question too. So remember that we're talking about an electron which is moving. Now, never mind the weirdness of the orbital shape of this electron. This electron is a particle which is charged. And like I showed you in the very beginning, a charged particle which is wiggling is going to induce some kind of wiggling in the electromagnetic field. It's a change in the electric field, which induces a change in the magnetic field, which propagates outwards. So if I have an electron which is jumping between energy levels, it's going to be changing the electric field, and therefore emitting some kind of light. Excellent question. So I want to make sure that I leave enough time, but I also want to make this statement by way of review. I want you to remember that the next time when you're looking at a picture like this, and you're looking at the stars in incredibly distant space, I hope that you'll remember that it's incredible what you're actually seeing anything at all. These seemingly unrelated forces of electricity and magnetism have conspired together to carry these tiny ripples of information across the vastness of space. These are incredibly minute changes in like electrons inside stars which are billions of light years away, trillions of miles distant from us. And yet this information is being dutifully carried to our eyes by these electric and magnetic fields. Without this incredible miracle of light, there might still be life here on Earth, but we would be completely unaware of all of the incredible behaviors outside of our world. Light, as a consequence of electricity and magnetism, these two seemingly unrelated things, is really a wonderful idea. But anyway, we don't have much time to talk about light. We have to get to this notion of stars. When you think about astronomy, you think about stars. Like, that's part of the name. And it's hard to tell with your naked eye on the surface of the Earth. When you look at these distant stars, they all basically look white to you because they're so small. But when you look at them through a telescope, or you look very carefully, you can see that each of these stars has kind of a different color. And we've been just talking about all of the wonderful information that color can transmit. So when we look at these, we can look at their black body spectrum. We can study them using these concepts that we were just talking about thermal radiation. And so even if we don't know what they are yet, we can look at their spectrum, the light coming from them, and we can tell that whatever they are, they have to be incredibly hot. And so our picture of stars is really based on our picture of this other thing that's in our backyard. It could just be a coincidence, but we have this like giant ball of hot gas right here pretty close to the Earth. And we can study that in a lot of detail. If we look at it through the spectra and we look for those absorption lines, we can carefully analyze what our sun is made out of, chemically speaking. We find that it's mostly made out of things like hydrogen, really light elements, and a little bit of helium in the interior, and deep, deep within the core, maybe some even heavier things than that. But we think that this is basically just like a giant ball of fire, emitting light due to its thermal radiation because of how incredibly hot it is. Why does it take that shape? Well, we think that it's just like the orbits in a kind of delicate balance, a balance between gravity pulling everything inwardly and the internal pressure associated with its intense heat pushing everything outwardly. If the strength of gravity were larger, it would get crushed and it would shrink. And if it grew much hotter, the pressure internally would rise and it would grow, pushing outwardly. But the sun would die out in just a few thousand years if all it had was heat to keep it going. It has some kind of internal source of energy, which is keeping it hot. So we want to answer this question, how is the sun making all of this energy, which is keeping itself from collapsing? And the answer to that question involves a diversion into nuclear chemistry. This idea of nuclear fusion is really at the center of our story of the sun and of stars in general. This is this concept that if you have an environment which is incredibly hot and incredibly highly pressurized, you can take individual atoms and smash them together at such incredibly high speeds that you can get new atoms. And as a byproduct of this, you can actually create a little bit of energy. A little bit of energy is translated from the mass of the original atoms into radiation, into thermal energy. You can take, for instance, 2 hydrogen nuclei and smash them together to create 1 helium, and a little bit of energy in excess. To do this, though, requires an extreme environment. You have to have incredibly high temperatures and incredibly high pressures. But this is what we think is found inside things like our sun. Imagine a ball of gas thousands of times the mass of the Earth, pressing in on itself. In the interior of that giant ball, you would find enormous temperatures. Things would be far hotter than we can ever imagine here on the surface of the Earth, and pressures which would crush you in an instant. This is an environment which is sufficiently extreme to create something like nuclear fusion, to create a source of sustained energy where you can take mass and translate it into heat to keep yourself from collapsing. So we can use the spectra of these very, very distant stars and compare them to our own sun, and we find that they're actually really similar. It seems like these very distant points of light are just like our own sun. Maybe they're a little bit hotter, maybe they have a little bit more carbon in their atmosphere, but overall, they seem to have the same nature and composition. So why are there so many of these giant fireballs out in space anyway? Well, to understand that, we have to think about how they would form. And that story involves these giant clouds of gas in space. This was a picture taken by the James Webb Space Telescope. It shows what's called a nebula. This is a cloud of gas and dust which is slowly collapsing in on itself. You can imagine a cloud of individual particles, each one pulling on one another due to gravity. Over thousands or even millions of years, these particles get closer and closer, and as they do, they heat up. The denser they get, the hotter they get, and the higher the pressure becomes. But gravity continues to contract them down and down and down until they become something like a star. Now, rather than just talking about this, I want to show you an animation. This was a simulation done on a supercomputer of what I'm talking about. We start with a cloud of gas, which is reasonably diffuse. We have no stars at all. And just over a few million years, this cloud of gas collapses down on itself to create these hot balls of gas. Once they're hot enough to start doing nuclear fusion in their cores, they can sustain themselves. They won't collapse down any further once they're able to start making energy on their own to counteract the force of gravity. But not all these stars are the same. Like I said, some of them are bluer, some of them are redder, some of them are probably hotter or bigger or something. There's actually an enormous diversity in terms of the different properties that stars can have. But let's just think about a couple of them. And what I want to establish is how these different stellar properties are related to one another. What can knowing the temperature of a star tell us about the star's luminosity? And how do we go about measuring these things in the first place? So, for starters, temperature is something that we've already built up some intuition for. If I can look at the spectrum of the star, I can measure where its peak wavelength is, which color is it emitting most preferentially. And like we established already, things which are hotter are going to tend to be bluer, things which are colder are going to tend to be redder. So all I need to do is to look at the spectrum of the star, and I can determine its temperature. But the temperature is not the only thing that I can learn. I can also think about how luminous the star is, how much light it's emitting per second. But be careful. Don't confuse this idea of luminosity with the idea of brightness. Brightness is how bright the star appears to you, not how much energy it's emitting. Imagine looking at, like, say, car headlights. If I were looking at a car which was right up in my face, it would appear much brighter to me than a car miles off in the distance, even though the headlights are actually using the same amount of energy in either case. The luminosity remains the same, but the brightness is different. So brightness is kind of like a function of luminosity and difference and distance. If I were to change the luminosity, obviously I would change the brightness. But I can also change the brightness by varying the distance. So if I can look at a star and I can say, this star appears this bright to me, I also have to figure out how to measure its distance if I need to figure out how luminous it is. But distance is something that we can measure as well. It's just one step out of the way. We measure distance using this concept of parallax, the same way that we measure distance in our everyday lives. Each of you, I assume, and correct me if I'm wrong, have two eyes. And if you navigate the world with your two eyes, you're constantly measuring distances to things, whether or not you realize it. I'm using both to figure out how far away things are. So let's think pretty critically for just a second about how on earth we do that. What is the wizardry going on in our heads that allows me to say, this thing is closer than that thing, just based on this bifocal vision? And to do that, I want to perform an experiment. Everyone take out your thumb and hold it at arm's length and close one of your eyes and cover your thumb, or cover the X with your thumb. So you should not be able to see the X. And then switch which eye you're looking through. Does your thumb seem to move? Good. So, your thumb is closer to your face than the X, so it will seem to be moving more. But now try this experiment. So notice how much your thumb moved in the first case, when it was at arm's length. It moved, maybe a couple degrees, right? Now move it much, much closer to your face. Does it move more or less? It moves a lot more, right? The closer that you make it, the greater this change in the parallax angle. Now, this is something that we use in our everyday lives to figure out how far things are, right? I can change which eye I'm looking through to, perceive each of you. And changing my perspective, just by this little amount, allows me to perceive distances. But this is something which works only for everyday scales. We can't go out into the cosmos and switch which eye we're looking through and expect to come up with very good estimates of distance. But we can use a trick. We can treat the orbit of the Earth as a giant pair of eyes. We can take a photo of a star against the background of very distant stars at one period of time, and then wait 6 months for the Earth to be someplace different, and take another picture. And we would see that this star, if it was close by, would move against the background of stars. Okay, so here's another review just to make sure everyone's staying with us. If star 1 has a parallax angle which is 2 times larger than star 2, is star 1 closer or further away from star 2? That means the change in where it appears to be between one picture and the next is 2 times larger for star 1. Is it 4 times further, twice as far, twice as close, or 4 times closer? Hold up your cards. Excellent. So I see mostly yellow C's, which is correct. If star 1 has a parallax angle, which is twice as great, the change in angle is twice as much, that means it has to be twice as close. So this is the fundamental assumption underlying all of our different measurements of distances. We can build distance measurements off of these using more advanced ideas, but this is the first rung of what we call the distance ladder. All of our other measurements of distance are based on this concept of parallax. But now we know how to measure distances to things in space, and so we can complete our notion of the understanding of luminosity. I can look at a star and I can measure its brightness. I can say, how bright does it look to me? And then I can measure its distance using parallax and understand how far away it is. Once I have those two pieces of information, I can solve for the luminosity. That's like imagining how bright would this star look if it was as close as another one. So now we have two really critical pieces of information. I know the temperature of a star, and I can know its luminosity. And now we can start doing some population studies. We can look at a huge sample of other stars in our local neighborhood and ask, what kind of relationships do they have with one another with respect to these parameters? What we're seeing here is a sample of different stars plotted in terms of their temperature and their luminosity. So, temperature is very related to color, like we've established. So, stars which are bluer are hotter, and stars which are redder are colder. So be careful not to read the axis on temperature backwards. But so in this scenario, we see a lot of stars are found on this kind of central line down the middle. We call this central line the main sequence. And this makes sense. Remember from before that temperature and luminosity are really related to one another. If I were to change the temperature even a little bit, like I said before, it would change the luminosity a lot. So if I have stars which have some kind of consistent form between one another, consistent nature between what they are, and I'm changing the temperature between them, I'm also going to be changing the luminosity. But temperature is not the only thing which is relevant for luminosity. Another thing which is really critical is surface area. Imagine that I had a much, much larger snippet of metal here that I was heating up. If I heated it up to the same temperature, but it was twice as large, it would be emitting twice as much light. The luminosity would be double, even if I had done nothing to the temperature. So if I really want to have a complete picture of how luminosity and temperature are related, I also have to think about this notion of surface area. I can't treat them as totally separate from everything else. Right? It could be that a very, very large but very cold star would have the exact same luminosity as a very, very small hot star. Right? One would just be emitting light over a much larger surface area, but less light per unit of area. So, another review. How do you expect that the star's mass affects the star's temperature and luminosity? This is asking you to guess something which is kind of in the future now. Do I think that massive stars, if I increase the mass of a star, is that going to make the star hotter or dimmer or colder or brighter or what? Which of these cases could it be? Which of these matches what your intuition tells you? Think about it for just a second. Is a more massive star going to be colder and dimmer or hotter and brighter? Let's hear what we think. We have a lot of diversity. So turn to your neighbor for just a second and try to convince one another of what the correct answer is. I increase the mass of a star. How is that going to affect how hot and how bright it is? Okay, so let's all come back together now and let's try this one more time. If I increase the mass of a star, is it going to become hotter or colder, or dimmer or brighter? Which of these answers do we think is most consistent? Okay, good. Now I see a lot more of these blue Ds, and that's correct. The more massive I make a star, the hotter it's going to be. This actually makes a lot of sense when I remember what a star is and what its relationship is with gravity. The more mass that I add to a star, the greater the gravitational pressure inwards. And the greater that gravitational pressure inwards, the more fusion is going to be happening in the core. Now, the more hydrogen atoms that we're converting into helium and energy per second, the more energy that we're going to have to be emitting per second. So, the more massive a star is, the faster fusion is happening. The faster fusion is happening, the brighter the star is going to be. And also, therefore, the hotter that a star is going to be. So how can we actually establish some of these relationships when it comes to mass? Well, to measure the mass of a star, we have to get kind of lucky. To measure the mass, we have to go back to the ideas we were talking about before with respect to orbital dynamics. But there are some stars which are pretty unique, stars that are orbiting around one another. And if we look at stars like this for an extended period of time, we can watch as they come closer to us and further away. Now, we're not going to actually see them changing their position in the sky very much, but using precision instruments, we can measure their motion due to the Doppler effect. As they orbit around one another, they'll spend a period of time coming towards us and a period of time going away. And using the Doppler effect, we can measure how fast they're moving. From this measurement and our understanding of orbital mechanics, as we talked about before, we can estimate the mass of a star. And if we plot the mass of these stars against their luminosities, we see the relationship that you were just predicting. The more massive a star is, the more luminous it is. The more gravitational pressure there is, creating fusion in the interior. And if I actually take a look at all of this data and I plot it in this logarithmic way, I can come up with another one of these power laws, another one of these proportionalities. It seems like for stars that are on this main sequence, stars that are along that central diagonal in that temperature versus luminosity diagram, it seems that for those kinds of stars, luminosity scales with mass to the fourth power. If I were to double the mass, the luminosity would increase by a factor of 16. Now, this seems plausible, right? Like you said, massive things are hotter. And, things which are just a little bit hotter, as we established before, are going to be enormously brighter. So this relationship kind of stands to reason with all of the other things that we've talked about so far. But we had to establish this by looking at data. Because we don't know exactly what's going on in the interior of stars, we can't just take our original understanding of light and physics and just throw it at that. We want to look at the data to be sure that we're getting this right. But so we found something really important, that the luminosity of stars scales with mass. It scales with mass to the fourth power. And that allows us to understand something else about stars, their lifetimes. Another interesting feature of stars is that they do eventually die. They run out of hydrogen in their core to fuse. And when they do, they can fizzle out, or as we'll see later, explode violently. But eventually they'll burn through all of the fuel that they have. What you're seeing here is the remnant of a star that exploded. But what we want to think about is how long will it take them to burn through all of the fuel that's available to them? Given what we just established, that luminosity is a function of mass to the fourth power. What we can actually see, just by this information alone, is that the larger, hotter, brighter stars are going to die sooner. And here's how we can figure that out. Let's think about these stars kind of like candles. If I have two candles in my hand, and one of them is twice as massive as the other one, and they're both burning with the same luminosity, which one of them do you think will live longer? Yeah, the bigger one, right? The more massive it is, the more fuel it has. So the longer it will take for it to work its way through that fuel, if it's burning the same amount per unit time. But if I were to say, if I have two stars that have the same mass, and one of them is burning much brighter, which one do you think will die sooner? The brighter one, absolutely, of course. So we can combine these two ideas to say that the lifetime of a star is proportional to both its mass and inversely proportional to its luminosity. The brighter the star is burning, the more fuel it's using up per second. And what's critical about this is that luminosity scales with mass, not just to the first power, not just to the second, but to the fourth. So let's say I have a star which is twice as massive as another one. That means that it has twice as much fuel to burn. But it also, according to this relationship, is burning through that fuel 16 times faster. That means that even though it has twice as much fuel, it's going to live an 8 times shorter life. And because the range of sizes of stars is incredibly diverse, the range of lifetimes is extreme. We can have O-type stars. These are the really, truly enormous stars that are absolutely massive and incredibly blue. These stars live for just 10 million years. Not very long in terms of even the history of life on Earth. Whereas stars like M stars, like dwarf stars that are incredibly small, incredibly red, incredibly dim, these stars can live for billions of years, hundreds of billions of years even. We theorize that they could live for 10 times longer than the age of the universe itself. That's how slowly they eat through their fuel. And as we discovered, based on these relationships we were talking about, it's the bigger ones that live shorter lives. They live fast and hot, and they die quickly. And before we end today, I want to talk about what happens when these massive stars die. So just take a second to watch this animation. This is a star which has run out of fuel in its core. It can no longer continue to fuse hydrogen into helium. When that happens, it's no longer able to keep up the pressure resisting gravity, and gravity will crush it down. When gravity does so, it can reignite fusion in the core for just a second, fusing even heavier elements, things like carbon and nitrogen and oxygen. And all of this happens in just an instant. When this star recollapses, it expands nearly instantaneously. And the amount of luminosity that it creates, the amount of energy that it generates from this instantaneous explosion is enormous. This single star can outshine almost all the other stars in the galaxy for this one brief moment. And when it explodes in this way, it distributes these chemical elements outwards to other stars and other neighboring solar systems. These are elements that are critical for the formation of life, things like carbon and nitrogen and oxygen, things that the universe did not have when it began, but which are absolutely essential for the functioning of our bodies and our society. Without these supernova explosions, we would not be here. There could not be life or complex systems anywhere in the universe. So before I stop and take questions, I want to leave you with this great picture. This is the story that we are leaving off with today before we continue on Wednesday. Gravity as the great sculptor, taking these clouds of gas and dust and collapsing them together to form systems of stars and planets. Within these stars, light shines, illuminating the nearby planets, light which is coming from nuclear fusion. We find ourselves on a planet just like the ones that are going to form in this simulation. An ordinary one at that, one which is indistinguishable from all of the other stars and all of the other planets that we can see. And we would not be here in our situation if it were not for the gravity that brought us together or the light that we receive from the sun. These are the ideas that are really central to our story of how we got here, that are really central to our modern mythology, the story that we've replaced, Zeus and Hera with. The story that we tell about how humanity came to be on Earth is shaped by these main ideas. That'll be where we leave off today. I invite you, if you enjoyed this lecture, to return on Wednesday for what's beyond this picture, galaxies, space-time, and the universe as a whole. But thank you all for coming, and I hope to see you then.